All right. So now let's go ahead and talk about this one. Potassium sorbate. They give us the formula. They give us the molar mass. It's commonly added to diet soft drinks as a preservative. A stock solution of C6H7O2 of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with 1.25 molar HCl. And I should have underlined 45 milliliters. Using both an indicator and a pH meter. The value of Ka for sorbic acid, HC6H7O2, is 1.7 times 10 to the negative fifth. Okay? A says write the net ionic equation for the reaction between KC6H7O2 aqueous and HCl aqueous. Now, keywords here is they already gave you the aqueous part, okay? Which means you already know when I put those in solution, they're going to do what? Dissociate. Let's pretend like they didn't give me the aqueous part for a second, okay? Let's say they decide to be mean this year, which they might, and not tell you that it's aqueous. How do I know this one is aqueous?
Because you got a K positive ion.
There you go. It's bonded to K positive. Remember, what are three things we know are always soluble? Anything bonded to potassium, sodium, potassium, sodium, and ammonium. Ammonium. Okay, that's NH4 positive. Okay, so K positive, Na positive, NH4 positive, I know is always soluble. Okay? Always and forever. Normally, nitrates are as well. They don't make you know that one, but normally your nitrates are as well. We'll go with it because they may do that to you. Okay? So those are normally your solubles. What else you need to realize are soluble are your strong acids and your strong bases. Those are always going to dissociate as well. Okay? So if I looked at HCl, if they didn't give me aqueous, I would know that's going to dissociate because it's a strong acid. Okay? So I would go ahead and write out what's going to happen in the reaction if I was you first. Okay? So I would say, okay, so KC6H7O2, which is aqueous, plus HCl is aqueous, is going to form what? KCl, which I know is going to be what? Aqueous, because it's bonded to potassium, plus the sorbic acid, which is HC6H7O2. That's not going to be aqueous. Why is that one not going to be aqueous? Because it's a weak acid. Does everybody see that? Huh? No. This is not a net ionic equation. Okay? Okay, so we got this far? Okay, that's good, because if you can get this far, then the next step shouldn't be a far reach for you. Okay? Everything that is aqueous is going to break apart. Everything. So it's going to break apart. This is going to be K positive plus C6H7O2 negative plus H positive plus Cl negative. Okay? Goes to K positive plus Cl negative plus this I know is not going to break apart because it's a weak acid. Okay? How do I know it's a weak acid? Because it's not one of my 6 strong acids. Yes? And excellent. Dylan pointed this out. And the Ka is very what? Small. Remember, what does Ka and Kb tell me? If I have a large Ka, I know the acid is strong. If I have a small Ka, I know the acid is weak. Because remember, Ka is essentially measuring how much of this is dissociating. Okay? Correct? Yes. All right, so now I've crossed out the things that didn't change. Yes? And so my net ionic equation is C6H7O2 negative plus H positive goes to HC6H7O2. And again, I can almost promise you there's going to be a net ionic equation on this test. I can almost promise you it's probably going to be in the acid and base section. And if it's not in the acid and base section, it's going to be on the electrochem section. It's going to show up in one of those two. Okay? In case you haven't noticed a trend, it showed up last time on the acid base in 2014, and it just showed up on acid base again in 2015. So if I was going to make a prediction, I would say it's probably going to show up on acid base again. They may change it. As soon as we start getting comfortable with it and picking up on their trends, they're probably going to change it. Okay? But we'll see. Everybody got that? Everybody got that? B says a total of 29.95 milliliters of 1.25 molar HCl is required to reach the equivalence point. Calculate the concentration of KC6H7O2 in the stock solution. Why is it crucial that they told me this was at the equivalence point? It's when moles of acid is equal to moles of base. Okay? How do I get moles of acid and moles of base? There you go. They gave me liters. They gave me molarity. And I know that molarity is equal to moles over liters, so therefore moles has to be equal to what? Molarity times liters. Yes? Yes, we've used this a ton of times. Okay? So, how many moles of the acid do I have? Has anybody picked up what we can do yet? Or y'all gonna make me go through all the big long steps?
37.44.
So we've got 29.95 milliliters times 1.25 molar. So that gave me what, Dylan?
37.4.
Didn't you do something with the molarity since it's a strong acid? Wouldn't it be the same or something? No, it wouldn't be the same.
So I've got 37.4 millimoles. So that means I must also have what?
37.4.
Okay, so that means I must also have 37.4 millimoles of my KC6H7O2. What did they tell me up here in this problem? That I used what? 45 milliliters. So therefore, I can divide this by 45 milliliters, and is that going to give me the concentration? Yes. So what's my concentration? Zero 0.832 molar. Did everybody follow me there? Yes? You would have gotten 1 point for that, and you would have gotten 1 point for that. Now, this is how they have it shown on their answer key that they sent all of us teachers. However, I probably wouldn't have solved it like that. I'm just going to be honest with you. If I would have saw that it was at equivalence point, I would have said M1V1 equals to M2V2. Okay? Where the molarity of my acid is 1.25 times the volume of my acid is 29.95 is equal to, I don't know the molarity of my base, that's what I'm solving for, times the volume of my base was 45 milliliters. And then I would have gotten the molarity of the base is 0.832 molar. the exact same thing. Because when you solve for the molarity of your base, this is your moles of the base here. Because the moles of acid and moles of base are equal. So that's it on top, divided by, you're going to divide by your 45.0. That's your volume of your base. So it's the exact same thing as what you did here.
Well, if we did that, would we still get a point? Or would we get counted off?
They gave you full credit for it in 2014 for doing it that way. So I can imagine they would in 2015 as well. They just didn't put it on. And it's up to you. You do whichever way is easier for your brain to think through.
They take millimoles in the exam because a lot of times they don't require moles.
Yes, they will take millimoles as long as you specify that it's millimoles. Now, I can't put this is 37.4 moles. I can't do that. But if you are showing that you know that's millimoles, they're fine with it.
So when you work out your problem, do you have to put the units as you're writing the numbers? Like
You don't have to. I just do it out of habit because it keeps me from messing up and not putting my units. That's just me. Okay. All right. C. The pH at the equivalence point of the titration is measured to be 2.54. Which of the following indicators would be the best choice for determining the end point of the titration? Justify your answer. Which one do we think we're going to choose? Huh? We're going to choose Thymol Blue. Okay. Why are we going to choose Thymol Blue? There you go. Because it has a pKa that is close to the pH at the equivalence point, right? So that means it's not going to change color until the equivalence point. And the last one for today, we'll do D. Calculate the pH at the half equivalence point. What do we know about the pH at the half equivalence point? Does anybody remember? We don't? I'll just tell you. At the half equivalence point, pH is equal to pKa. Okay. What does that P in front of the Ka mean? We're going to take the opposite log of the Ka. So pH is going to be equal to opposite the log of, what did they give me up here in this problem? Ka.
Oh, so pKa at the half equivalence point equals the concentration of hydrogen.
Yes. Okay. So the opposite log of 1.7 times 10 to the negative fifth. And if I put that in my calculator, then I get 4.77. Oh, by the way, in this problem up here, you got 1 point for the correct indicator and 1 point for the justification. pH is equal to pKa at the half equivalence point. So you could also, as Ish just said, you can also say the concentration of hydrogen is equal to the pKa at the equivalence point, at the half equivalence point. And that's something they may try to throw at you this year to throw you off. Okay. So in that case, I would just find the pH and then do 10 raised to the negative pH, and that would give me my concentration of hydrogen. Don't forget your homework tonight.